It's also about the copper-based shape memory alloy. It's about okay. I after completing my PhD, it was when the end of communism in 1981 was in Czech. I had to decide whether to go to the bank or to disappear somewhere abroad. So I disappeared abroad. I went to Japan. It was the Faculty of Engineering. Professor Tokuda invited me through the help of some scientists. So one day I left my family and disappeared to Mie University. And the only equipment they had was a machine for combined tension and torsion. So with my knowledge of shape memory alloys, I decided we will make but the sample was big like this, yeah? And then for combined and torsion you use tubes. So we bought a piece of the only shape memory alloy copper base which was available on the market was in Japan was this copper aluminum zinc mangan, big like this, and then we wanted to make the sample which was big like that, and in the middle the tube like 20 centimeters. And the main problem was to drill the hole into it. So the professor said to the students, just go, we had a lath here, so go there and drill it. So we tried and it didn't work. And then the professors came and spent there overnight and drilled the hole through the sample. So he managed it. I really admire it. After that, we asked the company, and company did it for us. It was not so difficult. So we had these samples of copper, aluminum, zinc, mangan, and we applied the combined tension and torsion to it. And so this was what we saw. This was the stress strain curve in tension, and this was the stress strain curve in torsion. And then the next problem was how to adapt the system for imposing the non-proportional loads, which means at first tension, then torsion, then unloading, and like that. So I had to play with the system. This was the sample which I spoke about, and the very first thing, like I was not so much in the mechanics, but I could see that if I multiply the stresses and strains over here from these two samples, I can make one sample. You know, I can convert these two stress strain curve into a single stress strain curve. So it's like an energetical criterion, but I have to use some constants over here, which I have no reason for them. So if somebody asks what is the reason for them, I say the only reason is I want to make such. So, okay. I thought if something is useful, let's use it. So I use it, and we measured the different kind of tests. So for example here, this is like at first torsion, then this is force. You know? So at first in torsion, then tension, then unloading, and here, and this is how the response looks like. So you have the reversible behavior like elasticity. If this would be only elasticity, the response would be same, would be square over here. But because it is super elasticity, the mechanism is not by Hooke's law, but by the motion of the interfaces. Here, when you apply the tension at constant torsion, the sample deforms more in the torsion, and reversibly on unloading. If you plot it as a tension and torsion curve, it looks like this. And if you plot it in this kind of combined using the coefficients, it looks like a single superelastic curve. So, well, if you look on this, the hysteresis width of this material would be like 200 megapascal. here it would be like 10 megapascal, and real hysteresis width is here only. Yeah? So we have the same energetical criterion that you can, if you have combined loads, you cannot evaluate the hysteresis. You have to plot such kind of equivalent stress strain curve to obtain the hysteresis. And is it this one? Yeah. Okay. So then you can imagine many other experiments. For example, this one we apply the torsion, and then at the same time the tension is increased and torsion is decreased. Yeah. So this would be the tension only. This would be and okay. So if I take this maximum response, so it is here. This is in tension. This would be in torsion, and in the equivalent stress, equivalent strain, this kind of reorientation would be such kind of internal loop. So at that time, it was in about 95. This was very first experiments in the world which was done in such a way. We were lucky because I didn't do it. I did it because there was the machine. Yeah, this was main reason. But it get the impression that this kind of reloading is in fact partial unloading and loading again. You know? And so this means that if you are decreasing the torsion and increasing the tension, the transformation is reverse, is reverse one. And this actually, when we look on the sample, we could see it. Some of the plates get back, yeah. And this is the major difference between the copper-based alloys and nitinol. And basically between the nitinol and most of the alloys. In copper-based alloys, it's very difficult to introduce because the phase which is induced is typically this beta prime phase, and there is no reorientation in beta prime phase. So this beta prime phase, if you do such kind of exercise, the only way how it can respond means to go back, to have the reverse transformation. But in case of nitinol, the martensite under stress will change the orientation, will reorient. And this makes a very big difference. So after that, we also made the experiments on nitinol, and the responses which we measure were quite different. Okay, so then we also did thermomechanical experiments. So here we have temperature also applied. The shape memory phenomena works very well. It's described in the article, and based on this, other people in the literature started to perform similar experiments on copper-based alloy, and the first general non-proportional SMA models were introduced by using the data of this. Also in France, some people did very nice experiments with the similar stuff. Okay, some of the phenomena are quite ridiculous. For example, in this test, we deform the sample in a complex way, and in the final unloading, final heating without stress, when you would expect direct reversion, again because of this, because of the lack of reorientation, what the sample does is that upon heating it deforms in reverse torsion and goes back. But it's only the consequence of this phenomenon that in the martensite no reorientation can happen. Yeah. So in copper-based alloys are actually very difficult to use in practice partially because of these phenomena. There are being the copper, aluminum, manganese in polycrystalline state being developed, and they suffer from the same problems. Okay. Yeah, we did also one more very unique experiments because we were in Czech. We were able to make the copper, aluminum, nickel tubes. So this is like 10 centimeter size. So we made a sample which is a single crystal and could be deformed in combined tension and torsion. So we brought it to Japan, and in Japan we made this test. And then in the very first experiments which we did, so it was just deformed in tension. So when I deform it in tension, suddenly the shear strain started to appear. And quite significant torsion angle, like 5 degrees, which was never observed on any plastic material, anything. And if you unloading, it went back. It was complete puzzle. Why, if you pull, it will start to rotate. You know? So we were really thinking about it, and again, it's a problem of this strain-compatible interface. If you imagine a tube of one crystal, single crystal, if you pull it over here, it will be like this, over here like that, over here like that, over here like that. So the habit plane would be inclined in different direction, and but you have one crystal. You cannot have it because the crystal doesn't allow for such kind of habit planes. So it will solve the situation by using different kind of variants which are induced here, 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 and here, and they must be strain compatible, but they produce the shear, and this shear creates the torsion. Yeah? So as far as I know, this was the only example of such kind of geometrically induced compatibility of Martensitic variants. Then some colleagues made the finite element modeling of this and confirmed. So this was published, but it's sort of unique phenomenon which only explains the importance of habit plane strain compatibility in case of single crystal experiment. Okay, and well, now because I wanted to make this talk consistent, so I will continue with experiments on copper, aluminum, zinc, manganese polycrystal, which we did later on, about after 2000, with in situ neutron diffraction technique and modeling. So please forgive me that I am now jumping into this neutron diffraction, but this is because I would like to complete the talk about the copper-based alloys. And so the why in situ diffraction studies? Because if we have the polycrystal and we are looking at processes which derive for phase transformation, the diffraction is the wonderful tool because it diffraction like X-ray diffraction. So you see the diffraction patterns which are reflection of planes in the material. And if you have two phases, austenite and martensite, you have different kind of diffraction patterns. So I can, if I pull the crystal, I can track this diffraction. And I use the basic principle which is shown in this right experiment. Hopefully it will start. So if you irradiate the sample by neutrons, you follow the diffraction over here, and you can see the position of the peak. So this is now in compression. I will run it again because I didn't have time to. But it will go automatically. No. Yeah. So now it's in tension, so the peak shifts to the right because of the tensile stress. This is if you apply because of the compression stress. Now you apply the tensile stress, it goes to the left. So it reacts to interplanar spacing. It is clear. And also you see here that the peak broadening the broadening is because you introduce the defects and internal stresses. So we can follow the peak shift and peak broadening with the lattice defects. And now, because we have phase transformation, we have peaks from austenite and martensite, we have also the integral intensity. So we can follow the integral intensity, peak shift to learn about the stress, and peak broadening about the defect. So it's a wonderful tool which can tell us a lot about the processes in the materials. In practice, it looks something like this. So you have the sample which you may heat. So if you heat and cool, you will obtain the transformation without stress, but you may also load it. And the information which is obtained is, if you have shape memory material, so you have the red would be austenite, the blue will be martensite. So you get the diffraction pattern here by detecting the diffractive signal both from the austenite and from the martensite. As I said, we can calculate the phase fraction from the integrated intensities. From the peak shifts, we can calculate the internal stresses, and basically the lattice in the materials are like so kind of sensors for phase fraction and stress. So with this introduction, I can we performed the experiments in England on engineering diffractometer engine, which at that time uses the Instron rig, put it into the neutron beam. It looks like this, and in fact there are two detectors. One is if this is the incident beam, this would be the diffracting planes. So this is we call it axial because the diffracting planes are perpendicular to the axis of the sample. While here the diffracting planes would be like this, so we call it radial direction. We got a different diffraction pattern. And so again, this was something relatively new at the time. Around 2000, this type of research only started on different kind of materials, mostly nitinol. We started with copper-based alloy, and the results look like this. So if you in this figure show the information from the peak shifts, because you are at the same time the intensity. These are the peaks. This is the austenite. This is the martensite without stress under large stress. So the intensities are changing. You see it, but also the peak positions are changing. And if you evaluate the peak position, you can see that in the elastic range. So from 0 to something like 300 megapascal, 200 megapascal here. It's approximately linear. This is as it should be in elasticity. If you have elastic deformation, the peak shift is proportional to the stress. This is the first line up to somewhere like 300 megapascal. But when Martensitic transformation starts, here it doesn't increase anymore. So you have such kind of response of the lattice spacing of 220 peak. But if you take another 220 is, where is 220? Somewhere here. And if you take another reflection like 400, you will get a response which is completely different. And again here, completely different. So what does it mean? This somehow gives the information how the families of equally oriented grains transform during the loading. Yeah, so this is the information which no one can obtain from stress strain experiments. Before I spoke about the strain, we can, in the same way, we can look on the integrated intensity, which is here, how it evolves with stress and with strain. So with stress, it's hysteretic. With strain, it's kind of sort of linear in the transformation range. So these informations, I know it's a little bit difficult to understand. So the only way how to understand it is to develop some kind of micromechanics models. And we used the knowledge which we had from the single crystal experiment, but without really knowing whether it is correct way or not. And this is here. So I said before that for each single crystal we can make a phase diagram which shows at which stresses the transformation occur, and then I know the transformation strain. This we measure. So we know the condition at which temperature it occurs, and we know the strain, so we know the response of the system for particular orientation. For cooling under stress, this is the strain temperature. Again, we will obtain such kind of response. So this is a model for a single crystal. The problem is that in the polycrystal, I have many grains and they are differently oriented. So if I have such kind of model for every orientation, but Václav Novák has already measured this, and this is the same for copper, aluminum, nickel, and copper, aluminum, manganese. So we had such kind of model for every kind of orientation and range of stresses, and here it is multiple transformation. So we had everything. The only way was how we connect two grains. I have two grains, so I can connect them in series or in parallel, which is the overlasting problems in the mechanics of materials, with this Taylor and the connection, and neither of them work. So we want to make some statistics. So then we came with the idea of such kind of, we call it aggregate polycrystal, where actually we have 4 domains, and they are connected partially in series and partially in parallel. And I can use this one domain as another domain on the next level, and on the next level, and on the next level, until something like 10,000 domains. And then we can populate each of these domains with the orientation. So for each domain, I know these responses. Even I can, if it's the bar and it has some texture, so most of the orientations are 1-1-1 oriented, I can impose the texture on such kind of aggregate. So we came with this type of model, which actually combined our knowledge about the anisotropy related with Martensitic transformation in copper-based alloys, and try to develop the model which would simulate the aggregate, meaning the polycrystal. And the result was surprisingly good. We find out that many of the experimental responses which could be observed in this diffraction experiment actually can be reproduced. So if you look on this diagram, so here the black is the macroscopic curve, and this is the behavior of differently oriented families of oriented domains. This is in this domain. You can impose only very small strains, and you have very high stresses. In this grain, you have very large strain, but the stresses are very low. But if the stress is low, it doesn't mean it really transforms preferentially in the polycrystal, because the stresses and strains, both of them combine together. So the model offers very nice insight into the mechanics of polycrystal transformation. So even though it's very simple and very discretized, it was welcome, and it is one of our highly cited paper, because it gives the idea how the shape memory polycrystal transforms under stress. One interesting point which I I like on this was that we were able also to explain the shape of the peak profile. If you look on this here, you know, we have, this is like the austenite peak, and when we load it and measure in every of these step, we measure the profile of this step. And then we look at it, how it looks like. Maybe I can use only this. This is from the model. This is from the experiment. So from the experiment, in the beginning, in the 0 up to the yield point, there is a main shift. Naturally, this is due to the elastic deformation. As the stress increasing, the peak shifts. But then when the transformation starts, suddenly the peak profile analysis of this gave us a very sharp peaks, which even though you increase the stress, it doesn't move more right. So what does it mean? This means that the lattice plane, even if you are stressing the material from 200 to 400, the lattice plane doesn't increase. The macroscopically the stress is increasing, but lattice plane doesn't. Why? No, but if you think about it, it's very clear. Yeah? In the material, there is some limit for local stress, and when you arrive at this limit, which is the Martensitic transformation, if the Martensitic transformation in 2 grains field this limit, it will start to transform, and the stress goes down. So that's the and then in the other part of the here from 6 to 10, the intensity goes down. And so when we did the prediction with the model, we obtained exactly the same situation in the this is in the actual, it's better seen. So at first the peak shift until the point 10, and from the point 10 you have the decrease over here. So even the peak profile analysis very nicely could, well, we didn't, there is also the change of the peak width, but this is more related to the intergranular stresses between different materials. But yeah.
Basically, from broadening, then it's becoming narrow. Usually it's called as crystalline kind of behavior. But
no, because normally the peak broadening is related to the dislocation density. So this is what is known in the field. Yeah. So if you have a material which deforms plastically, in the beginning the peak is narrow and then it becomes broad. This is the state-of-the-art knowledge. Okay. In this case, there are no dislocations. But we see the same phenomena, but no dislocation. So the question would be, what is the reason for the peak broadening over here? Imagine that this profile comes from, for example, 1000 grain. And if in each grain there is the same stress, the peak will be narrow. If in each grain the stress is different, the peak will grow. Yeah? So you have a peak width will grow. So you have a different mechanism for peak broadening. Forget about dislocation. Now the mechanism is the distribution of stresses within these families of grains. Yeah. So like if exactly you see here that in the beginning it was quite kind of broad, and at the end it becomes very narrow. So you may ask why. So as I said, yeah, you are loading the crystal and you have the break. And the peak shifts, and then comes to the break. Break is the phase transformation. Any domain which feels the stress will go down, will disappear from the spectra because it transforms to the Martensite. So as it moves, it becomes narrow. Because the volume is this, because yeah, it increase. If it becomes too narrow, it has to be wider. The intensity is not decreasing so much. In the beginning, you don't, because of this break, you know, and the break means that in some grains it cannot shift further, you know.
So this is one cycle we are talking, only the one part where we do different sections, right?
Yeah.
If we do repeated cycling, there is one nature which is being observed in SNA element, repeated cycle. The graph will shift. Yes.
This is actually 2 cycles. Yeah.
So what is the cause of that shift?
Stress, internal stress in the material, because in the we have this everywhere in shape memory alloy. If you make a first cycle, and this is very more in nitinol than in this material. If you make the first cycle, you introduce the phase transformation, but also some little plasticity somewhere. And this little plasticity, you can imagine, you have 2 grains, and one will deform plastically. And after unloading, this is longer, this is shorter, and what do you remain? You remain, it goes back, but at the boundary there is internal stress.
So like after hundreds of cycles, it kind of stabilizes itself. So that
Because if you, okay, so in this effect of the internal stress, we did experiments particularly designed for that on nitinol. You know? So in the like first, not one, in the first 2 or 3 cycle, the phenomenon is maximum. But after that, in tens or 100 cycles, it's less and less, so it somehow stabilizes. But what happens is that in every grain, you have some plastic strain mismatch, which introduce some internal stress. And then if you are loading, this internal stress sums with the external stress which you apply. And because of that, typically in the second load, you will have a lower stress. Why you have lower stress? Because if you load for second time, the internal stress help to the transformation to proceed, which are already inside your material. So if there is no plasticity, there should be no internal stress. But in this material, in copper aluminum, in case of copper aluminum nickel polycrystal, it will break because there is no slip, and the sample will break and you will have fracture. But in case of this material, you have some plasticity, so it can survive maybe thousands of cycles, and you have this phenomenon with internal stress, which we can directly measure. It's a beauty. You see it here. You know, we are measuring here. This is the what's the oh I forgot. It's not here. Okay, this is the lattice spacing of some lattice plane in austenite. So the macroscopically, the difference between the red and blue is something like 100 megapascal almost. No, how much is it? No, it's less. Yeah. But in case of lattice plane, the peak shift is exactly the same. Because the peak shift inside the material, it measures the external stress plus internal stress. So, if it answers your question, if you believe me in that, this is a very nice proof of that. This is a sonde which is gauge which is in the material, and it tells you that it transforms when the internal stress is 20. You know? And it's in the same in the first, second, and fifth, and 100 sample, because the phase transformation very nicely detects it. Okay, I am at the end. So this is, I'm not sure how I am in time. Ergia, could you look? It's fine? Yeah. Okay, I shortened it intentionally because we agreed that we will have a little bit. So this is the over the copper-based alloy. Tomorrow I will switch to nitinol, and for the rest of the time I will be talking about nitinol, which was my work in the last 20 years maybe. Thank you.